So today's lesson, honestly, is mostly vocabulary, but you're going to want to write some things down. So we're doing 6-1, radian and degree measure. So, angles. Well, how do we create an angle? First of all, we have to start somewhere. So that's what's called an initial side. Then we open up and create an angle here. So we opened up to a terminal side. So terminal side just means where you opened up to. Now, right here is an angle drawn in thin air. I can draw an angle in thin air, yes. But now if you see them say draw an angle in standard position, that means instead of just creating an angle in thin air, put it on an XY chart. That's all standard position means. So notice I have an XY chart. My initial side starts here, and then I'm creating my angle to my terminal side. So a lot of times they'll say, create an angle in standard position with a terminal side of 30 degrees. So does everybody see what that would mean? Standard position, you'd start here, and you would draw up to 30 degrees, point your arrow, and say 30 degrees. Okay, there are positive and negative angles. A positive angle is created when you have an initial side, and then you open up the angle counterclockwise. Or going upwards. It's easier for me to just think. I'm going upwards, so that's creating a positive angle. Now the arrow is what tells me that we know it's positive. You've got to be drawing arrows. A negative angle is going downwards or clockwise. So initial side here, we're then swooping downwards to create this angle. So notice that these are this is the positive distance, and this is the negative same distance. That would be a positive angle and a negative angle that are the same. Pretty straightforward stuff. Okay, this is a word that you may or may not have used before, a coterminal angle. These are very useful for us in our trig unit. A coterminal angle will have the same initial side and the same terminal side. So what that means, guys, is it's an angle that lands in the same position as the original angle. So think about it. If I start here and I go positive around here, and I add 360, won't I end right back up to that same arrow? Do you see how that would be a coterminal angle? It just hits the same spot, falls in the exact same place. So now look, if I take 30 degrees and I subtract 360, that would then put me back at the same spot. That's a coterminal angle. So I just added 360, and I can do that as many times as I want. So look, I could add 360, end up back at the same spot, add 360 again, end up at the same spot. I could add 360 and end up at the same spot. So do you see how there are unlimited coterminal angles? Okay. So, and then there are, once again, unlimited negative coterminal angles. I could subtract 360, and I'm going to end right back up where I started. Okay, so it says find one positive and one negative coterminal angle. So you would take 120 degrees. To find a positive coterminal angle, you'd add 360, and that would be starting here. We want to end up at the same spot. 480 degrees would land in the exact same spot as 120 degrees. So now to find a negative coterminal angle, 120 minus 360. Negative 240 degrees. You see how that's a negative coterminal angle? They would land in the same spot. You would be drawing the same angle essentially. So look at this one. A lot of people have a hard time with this. If we take negative 420 degrees, to get back into the positive angle, I would have to add 360, and I would still get a negative answer, wouldn't I? If I only added 360 once. So that would be considered a negative coterminal angle. But then I could add 360 again, and now I have a positive coterminal angle. So you can do it as many times as you need. Now everybody listen to why this is useful. We're going to be doing trig based on the unit circle. Isn't the unit circle from 0 to 360 degrees? So if I asked you to perform some trig on negative 420 degrees, it's harder to think about. Instead, you'd want to think of the unit circle and use positive angles. So you would add 360, and then boom, you would do the trig on that angle because it's the same thing. Does that make sense? It falls in the same spot. Does everybody see how that would be useful? Okay, cool. Hey, do these problems, ready, set, go. So So some more vocabulary, like I said, complementary and supplementary angles. So two complementary angles add up to be 90 degrees. Two supplementary angles add up to be 180. Now here is what tricks people. It has to be adds up to. It has to be the sum. It cannot be subtraction. You cannot do complementary angles with a negative and a positive. It has to be sum. So keep that in mind. Not all angles have a complementary or supplementary angle. Hey, let's look at, this is out of the book 44A. It says find the complementary angle of this. So the complementary angle would be something plus 3 equals 90. What something is that? 87 degrees is the complementary angle. Now a supplementary angle is that an angle plus 3 needs to equal 180. Yes. Very good. Now look down here. This one is 46A we're going to look at. Find the complementary angle. Well, what plus 130 equals 90? Won't it be a negative? Yeah. That will not work. So you would say there is no complementary angle. The supplementary angle would be 50, right? 50 degrees. Okay, cool. So 44B, same idea. Do you guys get the picture? Okay, cool. We won't continue then. Do these ones on the homework. These ones are like 290. I want to say this. So on the ACT, a lot of times they will have like x plus 2 is angle A, for example, and 2x minus 3 is equal to angle B. And it says these are complementary angles. So your truth statement would be this plus this equals 90, right? Then you'd solve for x. And then they might say, what's angle A? Now, if angle A was a negative angle, you would have to say it's not possible, right? So they would have that negative answer on there, which a lot of people choose because that's what you found. But by the definition of complementary, it has to be some. So on the ACT for that one, you would choose not possible or none. None of the above answers. You know how that's on there sometimes? So just keep that in mind. What if it was positive? You'd be good to go. Okay, moving on. Okay, so now this is where you really want to pay a little bit more attention so that this will actually make some good sense to you. Okay, awesome. So we're going to talk about degrees and radians. Now understand, a degree and a radian go hand in hand. They are equal, but they mean different things. You're looking at different things, but they are equal. So the degree is the measure of an angle theta. The degree is the actual angle. Now a radian is actually the physical length of the arc that angle opens up on. So look at my picture right here. This would be my angle, and this is my length of my arc, which would be my radian. So this angle opens up on this arc. So one is the physical length, one is the degree measure. So engineers are using the physical length, where mathematicians use the degree measures a lot of times. Okay, so 1 radian, where does that come from? I'm going to explain right now. I'm going to tell you. A radian, 1 radian by definition is when this happens. This is 1 radian. When you're creating an angle, you're opening up, and then finally you hit a certain point when this length right here, this physical length, is equal to the length of the radius. That's what creates a 1 radian. When the radius and the length of the arc are finally equal in length. So if this was at 3 centimeters, this length right here would also be 3 centimeters. Do you get what 1 radian is? Okay, cool. So now that's going to help us see where 2 pi comes from. Where 2 pi, we know a full circle is 2 pi, correct? Okay, now look, that's where it comes from. 2 pi radians is what we're looking at. So let me explain. You don't need to take notes right here. I'm just making sense of what a radian is to you. So look, we know that a full circle is 360 degrees, which equals 2 pi. But what does that mean? Well, I'm going to show you. So if I start right here, and I'm drawing an angle till boom, all of a sudden now that length and that length are equal, that's 1 radian, right? Now I'm going to keep going, draw again, and all of a sudden, boom, that length is the same length as the radius. There's my second radian. Does everybody see what I'm doing? Third radians, 4 radians, 5 radians, 6 radians, and then to finish off my circle, I've got to go this little teeny bit more. Does everybody see? So it's 6 and something radians, right? Just over 6 radians. Does everybody see? Type into your calculator, 2 times pi. 6.28 radians. So everybody, do you see something interesting? This is equal to this. This is the degree measure. This is the length of the arc. Now, a mathematician would use these two answers. An engineer, however, would rather have a physical length. So they actually, just with the radians, they multiply pi in. But do you see how pi radians and radians are equal? It's just one has pi already multiplied in. Cool, right? So that's where it comes from. Now, obviously, all circles have a 2 pi outside. So what's going to change it up? Because there are different circles of different size. The radius. So that's why, literally, circumference is 2 pi times the radius. It's the physical distance of the outside, and then you have to times it by the radius. Does everybody see how that would make sense? So that's where circumference comes from. Now, they call a full circle also a revolution. So they say there's one revolution. That means it went around the circle one time. So some more definition. You don't need to take notes here. We're not doing the unit circle today, but this is where the unit circle comes from, everybody. So one full revolution is going around the circle one full time. That's 2 pi. Now, on the unit circle, if you'll remember, it's cut up into 4 quadrants, right? So if you think about it, if you take that full circle and you divide it in half, then halfway around the circle would put us at pi. We already know all this, just trying to make some sense here. So now instead of having our full circle here, if we want to say, well, what's a fourth of that? Cut it into fourths. You would take 2 pi divided by 4, which is pi halves. That's why up to here is pi halves. 1 pi halves, 2 pi halves, 3 pi halves, 4 pi halves, right? 4 pi halves is 2 pi. Okay, cool. And then we could cut this up however we want, but on the unit circle, they cut it up in different ways, but pi thirds. So if we wanted to cut it up into 6, we could take 2 pi, cut it up into 6 pieces, and we would get 1 pi thirds. Does everybody see? We could go 2 pi thirds, 3 pi thirds, and so on. Does everybody see what I'm saying? Okay, so that's where the unit circle comes from. They're just cutting out 2 pi in special places. Now, all of our angles, or radians, same thing, are going to land in a quadrant. So quadrant 1, 2, 3, and 4. So if I said to you, what quadrants does angle 80 degrees land in, you would say quadrant 1. If I said to you, what quadrant does negative 80 degrees land in, you would say quadrant 4. Does everybody see? Now, you will have times when they say, what quadrant does 180 degrees land on? You would say the x-axis between quadrant 2 and quadrant 3. Okay, so everybody good with that? Now think about it, a coterminal angle, this is going to be really useful to us when we get into doing trig of really big angles or really small angles, like in the negatives. So if I said, find the, what quadrant some huge angle's in, can't I subtract 360 or add 360 to figure out where that lands? Okay. So you get it in the 1 or 0 through 360 piece. Does that help? Okay, cool. Let's do these. Okay, let's answer these questions. It says, sketch the angle in standard position. This is literally on the test. So watch what I would expect. So it says, sketch the angle in standard position. So you would draw an XY chart, then you would draw your initial side. Now this is negative 270 degrees. So aren't we going downwards? You've got to point your arrow in the correct direction. So we went right there, negative 90, didn't we? Keep going, negative 180. Keep going. Negative 270. So that's where it landed. So now I'm going to draw my terminal side. Now look, that is equivalent. It lands in the same spot as positive 90 degrees. So you could take that and add 360, because to me it's easier to graph positive angles, which is 90 degrees. So I could graph 90, but then it goes negative, because it's the negative one. Does that make sense? Kind of helps me. So negative 120. Let me just show you. That one was pretty easy, but let me just show you what I would expect. Okay. So we would go like this. That's negative 90. Now, if we went all the way to here, that would be negative 180. We need to go negative 120. So how many past negative 90 do we need to go? 30 more, correct? So I would draw this in, I would go like this, but then you have to tell me, because it's hard to draw it perfectly, I went 30 units from there to there. Does that make sense? I know you said it was negative because of the way your arrows are pointing. Okay, cool. Sweet. Now let's answer these questions. Determine the quadrant in which each angle lies. So negative 260, where would that land? Quadrant negative 260 is quadrant 2, over here somewhere, correct? Because this was negative 270, so it's right here more. True, yeah. Okay, what about negative 3.4? Quadrant 4, that's super easy. So what if I said, what quadrant does angle 1000 degrees land in? What do you use? Subtract 360, subtract 360, subtract 360 so you can figure out where it lands. Because that would be a coterminal angle landing in the same spot. Cool. Okay, now it is going to ask you to find positive and coterminal angles when it's written as a radian. Now remember, a radian is the same thing as a degree, it's just one is the outside length of the arc. So, we just said that if you have an angle, you can add 360 degrees, and if you have an angle, you can subtract 360 degrees to find coterminal angles. So now this is written as a radian instead of a degree. So what would be equivalent to adding 360 degrees? Adding 2 pi. That would be a positive coterminal angle. So take your calculator. Because they started in terms of pi, they want you to leave it in terms of pi. So take your calculator and just do 7/6 plus 2, math, enter, enter. Do not type in the pi part. What's a positive coterminal angle? Perfect. So 19 pi 6 would be landing in the same spot. Everybody good? So now you would do 7 pi 6 minus 2 pi. You would do 7/6 minus 2, and you get... What is it? Yep, negative 5 pi 6. Okay, cool. All right, now here's how we convert from degrees to radians and radians to degrees. It is hard for people sometimes to memorize which one goes on top, so I'm going to kind of help you see what to think about. So if you want to take something in its degree form and change it to the radian form so that instead of having a degree measure, you have a physical length, you're going to multiply by pi over 180. Now think about this. We're not changing the problem because isn't pi and 180 the same thing? So we're timesing by a 1 essentially, aren't we? We're just changing the format of it. We're not changing the problem because we're just multiplying by a fancy 1, but we're changing it to its physical length instead of angle. Now think about it. A lot of times people have a hard time. Which one goes on top, the pi or the degrees? Well, we need our degrees to cancel out, so degrees would be on bottom. So that would then convert it to its radian format. Now, pi radians you could find, and then if you're an engineer, you would then take and multiply pi in and get just radians. All right, so how do we take a radian to a degree? Same thing. You'd multiply by 180 over pi. Now, this will usually be written as pi radians, so it's easy to remember. I need my pi's to divide out, so pi's got to be on bottom in this case. There are times when they'll already have pi multiplied in, so in that case, you'd have to type it into your calculator. I'll explain by example. So just watch. These are so easy, you could just watch. Let's change this to the physical length, the radian. So we'd multiply by pi over 180 degrees. Now my degrees cancel out. So isn't that the same thing as this? 135 pi over 180. Take your calculator, do 135 divided by 180, math, enter, enter. 3 pi 4th radians. Everybody good with that? Now an engineer would then say, okay, what's that distance? You would take your calculator and just do it all the way to the decimal. Everybody good? Okay, right here, same thing, you multiply by pi over 180, so take your calculator, that divided by that. What is it, 3 halves? Perfect, negative 3 pi halves. Everybody good? Let's go the other way. So we're changing this to its degree measure. Now, why would this be useful? Because if I said to you, graph that, well, where the heck is that? I don't want to have to try to think about like the unit circle and radians as much. Isn't degrees a lot easier? That's when it would be kind of useful to say, let's just convert this. So we'd multiply by 180 over pi. so that my pi's divide out by hand. So then take your calculator, do 9 times 180 divided by 2. 810 degrees. So now that would be pretty easy to draw for the most part. Okay. All right, look at this one. We do the same thing, multiply by 180 over pi. So then my pi's divide out. So negative 80 divided by 2 is negative 90 degrees. Okay, 2 radians. This one used to throw me for a loop for some reason. What did we just say was the difference between that and that? Anyone remember? What? What? Anyone? We don't know the difference? This one, the pi is already multiplied inside. This one, the pi is not. Can't we take our calculator and just find out the radians by actually doing 9 times pi divided by 2? So this one has pi inside already multiplied in. So the same thing applies. You'd multiply by 180 over pi. But now do you see how we can't divide pi out by hand because it's multiplied in? You just need your calculator to do that part for you. So you take your calculator in this one and type in 2 times 180, and then you got to divide by pi. And your calculator will take the 3.14 and divide them out for you. Does that make sense? Okay. So how many degrees? 0.59 degrees. Not perfect, but that is an angle, right? Everybody good? Okay, cool. Do these problems off the homework. So, this is a true statement. If you have a central angle, now a central angle is created when you start at the center of the circle and open up an arc. A central angle equals its intercepted arc. So this is equal to this. So everybody look, if this is a central angle, and it is, and it's 35 degrees, then this length, or this arc, is also 35 degrees. So if this is 35 degrees and opens up on this arc, it's a central angle that equals its arc, and this is also 35 degrees. But what's wrong here? This circle is physically much smaller than this circle. So what's the difference? The radius. So if this radius is 5 and this radius of 10, all you have to do is take that 35 degrees and multiply by 5, and then you'll have the degrees that that's covering. Does that make sense? So how many degrees is that? Huh? 175 degrees worth of coverage here. Does that make sense, everybody? So then if I wanted the physical distance, couldn't I then convert it to radians? And then I could tell you exactly how many centimeters we're talking. 175 degrees worth of centimeters. Do you see how that's not useful as an engineer? So then you could convert it to radians. So then this we times by 10, so that'd be 350 degrees worth of distance of centimeters. So then you could convert it to radians. Everybody good? Okay, cool. So the length of an arc is our radius times theta. Length of the arc, S, is equal to radius times theta. Makes sense from what we just talked about. So it says the circle has a radius of 4 inches. Okay, good to know, 4 inches. Now this is what's cool. If we literally traced out a piece of string 4 inches long and created a circle, right? Created a circle. It says find the length of the arc that intersects by a central angle of 240 degrees. So if we went around 240 degrees worth of distance here, how much physical outside distance are we talking here? How much string would actually measure out? Well, let's talk about this. So S is equal to radius times theta. The length of that arc will be the radius, which is 4 inches, times the angle theta, which is 270 degrees. How many inches of string? So you would do 4 times 270, which is 1080 inches worth of string. Now that's not useful. So then you would convert that to radians. What did I say? Oh, I did 270 on accident. 240. 960 degrees. So now take that and multiply by pi over 180 and give me a actual decimal. How many inches? What is it? So you guys, literally, if you measured it out and you traced out 16 and wrapped it around that circle, that amount, it would match perfectly. Cool, right? You can actually do it. It's like real world actual measurement. So it's so cool. Okay, cool. Now here's area of a sector formula. This should be really easy to memorize. Honestly, here's why, because it makes complete sense if you'll listen. So we know that the area of a full circle is pi r squared. That would fill in the entire circle completely. Pi r squared. Now finding the area of a sector means just find the area of only a section of the circle. Instead of the full circle, I only want the area of a section. So look at the formula, almost identical, but instead it says take the section out of 360 and then we want the area. Does that make sense? Theta over 360 times pi r squared. We want this section out of 360's area. Now here is the catch. To use the formula as this, since this is 360 degrees, you have to only input something as a degree, not a radian. So if they gave you a degree, if they gave you a degree of pi halves, you would first have to convert it to degrees and then find the area. Does that make sense? Or there is another formula, and I'll show you where it comes from. It's identical to this. So everybody, if you want to type something in radians, if you think about this, isn't theta over 360 the same thing as theta over 2 times 180 degrees? Well, now isn't pi and 180 equivalent? So we can divide those out. And now do you see how I got rid of the degrees? So now it's a radian. This is the formula for radians. They're equivalent. So now you could type this one in radians. You could calculate it that way. I don't like to memorize both. So I just know this one, and anytime I'm asked to find the area of a sector, I convert it to degrees and then do it. But that's just me. Or you could like just derive that formula and think about it. Okay, cool. So everybody, it says, this is Farmer John comes to you. Okay, never mind. It's a golf course, it says, right? Let's see. Okay, a golf course owner comes to you as a mathematician and you told him that you got A's in your honors class, and he says to you, well, I got a sprinkler that I have, and this is literally some math you have to do. I have a sprinkler sitting here and it's spraying out 70 feet. And think about how a sprinkler works. Doesn't it go like this? And then it goes back like that. So he says, how much area is getting covered by water here? How much water is getting covered? How much area of water? So you say, well, that's just a section of a circle. So you say, okay, so it's theta over 360 times by pi r squared. So what's my degree measure? We're covering 120 degrees out of 360 degrees. Pi, and then our radius is 70 feet squared. So we're going to be able to tell our golf course owner exactly how many square feet he is covering with the water here. So don't type in pi, because I want to have the mathematician answer as well as the Farmer Joe answer, the engineer answer. So you would tell a mathematician the answer, you would do 120 divided by 360 times by 70 squared. Hit math, enter, enter. I want the answer in terms of pi as a mathematician. Without pi multiplied in. Over fraction. Colton's the only one doing it, huh?
Yes.
You can't type pi. Oh, did you not type pi in? And it's still doing it? I swear that that's what I got too. Okay, perfect. So that's what you say in feet. Oh, it's feet. It's feet squared or square feet, right? Now, but if you said that to the golf course owner, he'd be like, what are you talking? What do you mean pi? And you're like, okay. Fine, you're right. You don't know what I'm talking about. Let me just give it to you straight. Now type in the decimal. How many square feet? Point 0.27 feet squared. So you can tell them you're covering around 5,131 square feet of grass when you're spraying this huge sprinkler. Does that make sense, everybody? Okay, sweet. That's the end of the lesson.